Alright guys, how's it going? Richards here. So today I'm gonna continue comment on the alum crystal growth. As you can see that the objective to grow a huge alum crystal failed due to some reasons. I think the most important reason is that when I get the solution, I actually shook the solution for quite a bit, but then vibration causes like nucleation process, and then so that the entire process speeds up, and then that's why I didn't get a huge like crystal, but I still got some like crystalline structure on the side of the container as well as on the bottom, so it's not too bad. I got some like I don't know scattered crystals instead of a huge crystal, but I mean it's worth a shot. Anyways, so how do you grow a crystal from a saturated alum solution? Is by slow evaporation, because like slow evaporation, then a crystal will start growing at the bottom at the bottom of the little vial, and then it essentially like slowly but surely like nucleation take place, and then more crystals will start gathering around the nucleus crystal, and then so that the crystal will generally become like bigger and bigger instead of like all those scattered small particles. Okay, and slow evaporation essentially prevents too many small crystals to grow. And in my room, I don't know if my room is too warm or not, but that will also like contribute to like faster evaporation. I mean, I'm using cream wipe. I'm not using a normal napkin, so that part would not be the source of error here. Anyways, let's move on to the scientific significance of despacing. So, despacing is like the repetition in a periodic arrangement of atom, means like there are many sets of parallel planes of atoms, and then each set of parallel planes has a consistent distance between a neighboring plane, and the distance is the despacing. So the spacing angles between planes enable us to reconstruct the entire crystal and figure out where the atoms are. And the X-rays are just the right length to interact with those planes. It's discovered by a British scientist in Oxford University. Anyways, X-rays are just the right wavelength to interact. Longer wavelengths bounce off, and the smaller will smaller. Wait, hold on, my mistake. So like, a large wavelength will like go through, and then like smaller wavelength will bounce off. So since like the planes are parallel, if they bounce off at the same angle, then they'll emerge at the same angle. So like solid have like different layers, and then so like if the longer wavelength goes through and the smaller like already like bounce off, then like they will essentially look like this. Like the smaller one bounce off right here, and the larger one bounce off like on the bottom, and then there's a certain distance, which is half the half life difference, like for them to be in phase, because this one essentially like just like bounced off way much earlier than this wave. Anyways, so according to calculation, the significance d is that like 2d sine theta. Theta is like the angle that the light goes through, should equal to like delta L, which is like the difference in like the path length. Anyways, so like for the crystals to be in phase, like the 2d sine theta value need to equal to be an integral multiplication of the wavelength if they want to be in phase. That's just like how a wavelength works. So the calculation right here for the alum crystal crystallization is that the 2 theta is at its peak when it's at like 20.3 degrees. So the angle would be 10.15 degrees. And then if we use this equation right here, 2d sine theta equal to n times lambda, 2d sine 10.15 equal to like n times 5 nanometers, and assuming the average wavelength for X-ray is like 5 nanometers in this case. And then the distance in the end after some calculation would be just like 14.33 n nanometers. So any multiplication of like 14.33 would be the path distance between alum solid layers. Alright, That's about it. Thanks for watching.